Okay, I'm going to have this video reviewing how to do this basic forces review. So let's start with this first one. This box is moving to the right and slowing down. In which direction is the acceleration? So the answer to this one is left. And the way we can go about this is I'm going to draw some velocity vectors. You don't have to do this, but I'm just going to draw them. So if it's going to the right and slowing down, the velocity vectors would look like this, going to the right and getting smaller and smaller. So the idea is that, well, if it's moving to the right, but those arrows are getting smaller and smaller, then the acceleration has to be in the opposite direction of the direction that the velocity is, right? So it's moving right and slowing down, you should have an opposite direction acceleration, which is to the left, right? If it was speeding up, then you'd have in the same direction, which would be to the right, okay? So that's number one. Number two, in which direction is the net force? This is also going to be to the left. Remember, according to Newton's first law, net forces are what cause acceleration. So whatever the direction the acceleration is going to be the direction of the net force. Okay? Now, time to draw a free body diagram. Okay? First thing we do is, well, I'm going to first have a gravity arrow. Gravity always points straight down. Okay? And then you look for things that are touching the object. I see a flat ground touching the object, so I'll draw a normal force arrow. Normal meaning perpendicular to the surface that's causing it. So if the surface is horizontal, I will draw a normal force that is perpendicular to that, which is straight up. Okay. Flat surfaces can also always apply a parallel force called friction. So that can either be right or left. And if you're wondering whether it's right or left, well, if there's the only other force that could be acting on this thing because there's nothing else touching it, then the only other force has to be to the left. Why? Because it needs to match the net force that you answered in number 2 here, right? So this is going to be the force of friction in this direction. Okay? Nothing else is touching it, so that FBD is done. Okay? All right, last question, number 4. If the friction were to suddenly disappear, what would happen to the motion of the box? Well, if the friction were to suddenly disappear, your FBD would only look like this. Sorry, this is a pretty bad arrow, but okay, it would look like that. These two forces would cancel each other out. Balanced forces means it would move, let me see if I get this font color right, in a straight line at a constant speed. Okay? So moving to the right at a constant speed, whatever speed it was going when the friction disappeared. Okay? If you said it were to stop, that would be incorrect. All right? The friction is what's causing it to slow down. So if you don't have any friction, it'll keep doing whatever it wants to be doing at a constant speed in a straight line. All right? Okay, so that was the easy one. Let's move on to the next elevator problem. Okay, person in the elevator standing on a scale. The person notices the scale is showing a number higher than its weight. All right, this one's a little bit tricky, but let's start with number 1. Draw an accurate FBD of the person. So once again, I'm going to put in the gravity arrow. A lot of people mess this one up because they kind of misread what's touching the person. So if you look at what's touching the person, the only thing that is touching that person is the scale. That's it. The elevator floor is not touching the person. The scale is touching the person. So you don't want to draw 2 upward arrows, one from the scale and one from the elevator. There is only one upward arrow from the scale itself. And you can call that a normal force if you want. That is a normal force from the scale. So I'm going to write both. If you just said normal force, if you just said scale, it's fine. But I'm going to say it's the normal force from the scale. Okay. Okay, so this is the normal force from the scale. And that's it. There's nothing else. Okay. Now it says, this statement right here, the person notices that the scale is showing a number higher than his weight. Remember, weight is, let me see, weight right here is another name for the force of gravity, okay? So when I say the scale is showing a number that's higher than gravity, what I'm saying is that this upward arrow is bigger than that downward arrow. So if I want to draw this accurately, I'd have to draw the upward arrow bigger than the downward arrow. Okay, this is what an accurate FBD would look like. So right here, this was a rough FBD. An accurate FBD looks more like the second one I drew. Okay. So then now once you know the second one, you can sort of see this FBD as unbalanced up, which means it's accelerating up. So I think some people would say it would be moving up. That is incorrect. It is accelerating up. Whoops. Accelerating up. And remember, accelerating up can mean two things. It could be moving up, slowing, speeding up. But it also could be moving down, slowing down. God, man, I can't type. Slowing down. All right? So those are the two possible motions that it could be doing. Okay, let's move on to the next one. All right. A, draw an FBD. In the future, I'm not going to ask you to draw an FBD. If you recall, you always draw an FBD as the very first step. Whether I ask you to or not, you always draw an FBD. Always draw an FBD here, okay? So your FBD should have looked like your standard 4-arrow FBD, okay? Normal force, gravity, and the two pulls from either side. All right. I'm not going to label mine because I'm trying to use my trackpad, and writing with my trackpad is pretty bad, but hopefully you guys understand what that is. So I'm just going to skip over a proper full FBD, okay? Set up your force equations. Remember, these two are your force equations, all right? So when you look at the x direction separately from the y direction, aka the horizontal direction separately from the vertical direction, all right? So for example, for this x direction, you should only look in the horizontal direction. And you see these two arrows right here. So right here, this x direction should have the forward arrow and the backwards arrow. So you can call it rope 1 and rope 2. All right. So for example, if I call this, or tension, if I call this tension 1 and tension 2 here, all right, then my force equation would say tension 1 minus tension 2. And the reason it's minus is because they're in opposite directions. Okay. So that is a 2 there. I'm not sure if it's hard to read. Okay. So that's a 2 there. Okay. So they definitely have to be minus. All right. Now, you could have done tension 2 minus tension 1 if you chose to make left positive. Okay. I'm choosing to make right positive. So I'm going to do tension 1 positive, positive tension 1 minus tension 2, right? Now you can go ahead and plug in numbers if you want. You could do 40 minus 15, right? Divided by 3. Okay. And that would actually be the answer to C, all right? So 40 minus 15 divided by 3 is, what is that? 25 thirds, all right? You could have written that in decimal, of course. And that's going to be meters per second per second. Don't forget your units of acceleration, meters per second per second. All right? And in the y direction, you would have normal minus gravity. So you have normal minus gravity. And once again, you could do gravity minus normal if you made down positive instead of up positive. Okay? So either one is fine, but it definitely has to be one minus the other for sure. All right, and that's also going to be over the mass. All right. Now in this case, since you know it's not moving in the vertical direction, you would actually plug in 0 for A. So I'm just going to plug in 0 for A here. Okay. Now you don't really need that for part C or part D, really. You only really need the first one for part C. Okay. but I want you to set up anyways, just for practice sake. All right, and then part D, this is one of those three kinematic equations. Remember, you had the velocity equation, the position equation, and the timeless equation. So you have to choose one of those three that makes the most sense. All right, so does it involve time? Yes, it involves time because I have 10 seconds here. Does it involve velocity or does it involve position? Well, I'm asking how fast it's going, so this involves velocity. So I'm going to use the velocity equation. And I plug in my numbers. And if I plug in starts from rest, 0. V final is what I'm looking for. A is my acceleration and T is my time. Then I can solve this out. And I will get 250 over 3, whatever that is. All right. If you, like I said, if you did this in decimals, it's fine. I just don't feel like taking out my calculator right now. So I'm just going to leave it as a fraction. Okay. All right. So let's go into the next one. Okay. So if you do this one properly, this acceleration should be, let me see if I do this right. So 30, okay. All right, I think you should get 3.06 if you do this correctly. All right. And once again, do all your steps, right? FBD, normal, gravity, and finger, or you can do hand. You can say push as well. Once again, I usually like to name it with the name of the object that's touching it. So that looks like some guy's really fat finger there. So I'm going to call that finger. And maybe you forgot what this meant, but this mu means there is friction. Okay. So there's definitely friction. Okay. Now, you're just going to set up your force equations from here. Do you need both the horizontal and the vertical? I don't think you do. Although you probably want to know how to calculate these numbers right here for all of them. Like, for example, gravity is going to be mass times 9.8. So gravity is going to be 5 times 9.8, okay? Newtons. All right, normal force, in this case, should be balanced with gravity because it's not moving vertically and there's only 2 vertical forces, so they need to cancel each other out. So this is going to be the exact same amount, right? 49 newtons. 5 times 9.8 is 49, right? Okay. And then you can set up your force equation for the horizontal direction. So you're going to do finger, right, minus friction. Oh, this writing is pretty horrible. Okay, but over mass. I think you just, now, if you don't remember how to calculate friction, you have to recall that friction, the formula for friction is mu times the normal force. It is not mu times gravity. It is mu times the normal force. All right. In this case, normal force is the same as gravity, okay, but it's not generally gravity. It's mu times the normal force, okay? So you calculate that, and so you're going to get 0.3 times 49. All right, oops, that should be at times 49. And I think if you do that, you get like 14.7 or something like that. 0.7 newtons. All right, so then you just plug those numbers in here. This is going to be 30 minus 14.7 divided by 5, and you'll get this acceleration that I found up there, okay? And then this is another one of those kinematics equations, all right? So just choose the right equation, either velocity, position, or timeless, right? Go through your same progressions. Doesn't involve time, doesn't involve velocity, doesn't involve position, okay? And I think if you do this properly, you'll see which equation to use. And I'm not going to go to the details of this one, just because this one's not too difficult. Hopefully you guys can figure this one out. And if you do this correctly, you should get like about 2.29 seconds, okay? Because it looks like your initial velocity is 3, your final velocity is 10, your acceleration is 3.06, and you just solve for time, okay? All right, last one. Vertical bucket problem. These vertical problems are oftentimes the most difficult, or not difficult, ones where people make the most mistakes. So let's sort of see, okay? Looks like it starts from, starts from rest. It was moving, is moving up and slowing down. So moving up, slowing down, that'll tell us the direction of acceleration. If it's moving up and slowing down, that means, well, the slowing down tells you it's the opposite direction of the motion. So that means if it's moving up but slowing down, the acceleration should be down, okay? The size I need to calculate using your kinematic equations, all right? Either velocity equation, position equation, or timeless equation. Looks like it does involve time. Looks like I have two velocities, so I'm going to use the velocity equation. Vf is equal to v naught plus at. And if you do this properly, let's see, the final velocity slows to a stop is 0. Initial velocity is 2. Acceleration is what I'm trying to find. 4 seconds is the time. If I solve this out, I will get negative 1/2 meters per second, all right? Now, what does the negative mean? Notice that with this choice of 2 right here, positive 2, I decide to make up positive. So it's actually pretty important that you realize, especially with these vertical ponds, as soon as you plug a number in here, I've chosen a reference frame. Now, you should probably choose a reference frame before you even start plugging in numbers. But implied by my choice of 2 here, positive 2 is that I made up positive, right? Because I called this positive 2 up, okay? So up is positive. And so what does this negative mean? That negative just means down, which is the same thing I got here, okay? So you need to watch those signs and understand what the signs mean, okay? All right, now I'm going to draw an FBD of the bucket. Hand looks like it's touching it, and gravity's touching it. This is going to be a rough FBD. I can adjust them later in order to make it accurate. Okay, so it's hand up. That should say hand, by the way. Hand up, gravity down. Now to make it accurate, I need to make sure my acceleration is down. So I need to fix this to make sure it's unbalanced down. So it looks like I could extend the gravity arrow, but just if you remember, I like to not change gravity because gravity never really changes because it depends on the mass of the bucket. So the mass of the bucket didn't change, the gravity doesn't change. So what I'm going to do is I'm going to adjust the other arrows to fix it. So the only way I can have an acceleration down is if the F of the hand is smaller than the F of the gravity. Okay? Now it's time to just plug in my force equation. There are 2 ways you can set this a force equation, all right? One way is to do hand minus gravity. One reason why I might like to do hand minus gravity in this case is because I've already decided over here that up is positive. So that means I'm going to call that the positive one and that the negative one. Okay, so I'm going to do hand minus gravity. But if I do that, I need to make sure I plug in negative 1/2 for A here. Okay. Now, so if you do that, negative 1/2 is equal to hand minus gravity, gravity being 5 times 9.8, which is 49. All right, over 5. You solve this out properly, okay, you will get a hand force that is definitely smaller than 49. So you should get, what is that, 46.5. Now, if you got something larger than 49, say my guess is a lot of people might get 51.5, well, you should automatically know something went wrong, because if you drew this accurately, there's no way that can be 49 and that can be 51.5. All right, this has to be smaller than that. Okay, so if you got something larger than 49, usually it's because you weren't careful about your signs. Now, I want to point out this is not the only way you could have done this bottom problem. You could have actually decided to make the gravity arrow the bigger one. So you do gravity minus hand. All right, so you're making down positive. That's totally fine too, but then what that means is that your acceleration will actually be positive, because you're now making down to be the positive arrow, which means that acceleration of 1/2 is actually positive. Okay, and then so you'd have 49 minus hand, and if you do this, you will also get 46.5. All right. So just be really careful about your sign setup here. All right. These are the only two ways you can do this last one to get the right answer. Okay. So that's how you do these review problems. Hopefully that was enough to actually remember how to do this. And if you now totally understand how to do all of these slides, then you should be well prepared to learn about the next unit, because it's basically feel very similar to what we just did. The next unit is going to feel very similar to what we just did. All right. Thank you very much. Bye.